Hello everyone, we are from RV College of Engineering and today we will be presenting our experiential learning topic quasi-solid electrolytes for ultra-stable, flexible and wearable batteries. Our team includes Sarthak Gupta, Ashutosh Joshi and myself Sudhanshu Sekhar. So let's begin by understanding the need for such advanced battery technologies. So, in recent years, flexible and wearable electronics have become increasingly popular, from smart watches to health monitoring patches. These devices need batteries that are safe, long lasting, and flexible. That's where quasi solid state zinc ion batteries or QSS ZIBS come into play. These offer high ionic conductivity as well as flexibility, biocompatibility, and enhanced safety. Our paper specifically focuses on bio-inspired polymer electrolytes, suppression of zinc dendrites, hybrid hydrogel designs, and crucial aspects like interface stability and ionic transport, specifically in systems like MnO2 zinc, known for long battery life and high performance. Next slide. So, what exactly are quasi-solid electrolytes? These are hybrid systems that combine the benefits of both the liquid and solid state electrolytes. Imagine a liquid electrolyte trapped within a gel or polymer matrix. This setup offers both high ionic conductivity and mechanical strength. QSSEs consist of two main components. The first one is liquid phase. It's usually aqueous or organic electrolytes like zinc sulfate. These handle ion transport. The second component is solid matrix, which is made from polymers like polyvinyl alcohol, polyacrylamide, or polyethylene oxide, or nanocomposites like MOFs, which stands for Metal Organic Frameworks, or halosite nanotips, which provide structure, flexibility, and dendrite separation. On the right, we can see an image. In this, a liquid electrolyte is trapped within a gel or polymer. This structure ensures both ion movement and structural integrity, making it ideal for flexible, high performance batteries. Next slide. So now you might wonder, why not just use solid or liquid electrolytes? Why we are using the combination of both? So well, QSSs bring together the best of both. They enable safe ion transport even when deformed, preserve function in flexible devices, support interface stability, reducing internal resistance, deliver ionic conductivity comparable to liquids without the leakage or flammability risk. Plus, QSSs can be stretchable, foldable, and even self-healing, things solid electrolytes usually can't manage. So, they truly are a sweet spot between performance and safety. Next slide. So, from an electrochemical perspective, QSSs offer several benefits. They have a wide stability window, meaning they can handle high voltages. They suppress dendrite formation, especially in zinc ion systems. QSSs are non-flammable, leak-proof, and resist degradation also, which is great for human body applications. What's more, they can be fabricated using various methods like from in situ polymerization to gel casting. We can do freeze thaw methods is also there, and even 3D direct ink writing is there, making them adaptable to different battery shapes and sizes. The solid matrix also play a key role in this. It physically blocks dendrite growth, which prevents short circuits and help extend battery lifespan. Next slide. So now let's compare the three different types of electrolytes, that is the liquid, solid and quasi-solid. So here we can see the ionic conductivity. Liquid electrolytes have high ionic conductivity whereas solid has low, and the quasi-solid is comes from the moderate to high. The same is the case for mechanical stability, where liquid electrolyte mechanical stability is low, solid is high, and the quasi-solid is from moderate to high. In the same way, flexibility, if we talk about flexibility, liquid electrolytes provide moderate flexibility, solid provides low flexibility, whereas quasi-solid provides high flexibility. When we talk about dendrite separation, in quasi-solid dendrite separation is very good, solid provides good dendrite separation, and liquid provides poor dendrite separation. So here, what we see, QCC strikes a perfect balance, good conductivity, excellent flexibility, and great safety. Now, next slide. So now we will talk about the fundamentals of quasi-solid state electrolytes, its composition and materials. So QSCCs are made up of two main components. That is, first one is solid matrix such as PVA, uh, polyvinyl alcohol, copper carrageenan or MOFs. Second one is combined with a confined liquid electrolyte such as zinc sulfate, zinc chloride. So the materials can be categorized as natural polymers like cellulose or kappa carrageenan, synthetic polymers like polyvinyl alcohol and polyethylene oxide, and inorganic additives like MOFs and silica, which help improve both the strength and ionic mobility. So these combinations help prevent electrolyte evaporation, form a stable ACI layers, and suppress dendrite growth. Now next slide. So now we will see the role of each components and ion transport. Let's now understand how each component contributes to performance. The liquid phase is responsible for high ionic conductivity, whereas the solid matrix ensures mechanical flexibility, structure support, and stops dendrite and leakage. Now we will talk about the ion transport mechanism. Ions move through liquid filled pores in the polymer. Their movement is supported by polymer ion interactions with polar groups like hydroxyl or ether. This allows for conductivity in the range of 10 to the power minus 3 to 10 to the power minus 2, which is almost as good as liquid electrolytes. So now next slide. So now this slide contains one diagram which shows how ionic liquids are embedded within a polymer matrix. We can see here cations and anions move through the gel structure. The cross-linking points give the matrix both mechanical strength and electrochemical stability. Such a structure makes QSs ideal for flexible, safe and long-lasting batteries, especially in wearable applications. Now next slide.
Okay, so we'll now look into the fabrication strategies which are there to form this quasi-solid state electrolytes. So there are various strategies we'll discuss one by one. So to begin with, the first one is polymer-based QSACs. So it is most fundamental method used for polymer-based matrix. So these involves like hydrophilic polymers such as PVA or polyacrylamide PM or polyethylene oxide PEO. So these are natural materials like a keratin. So these polymers are selected because they contain the functional groups like hydroxyl and amide groups, which coordinate with the metal ions, such like as we mentioned in the starting, it is Zn2 plus ion, Zn ion batteries. So these coordinate very well with the metal ions, which enhance the ionic conductions. Also, the synthesis typically involves dissolving the polymer and salt in water or solvent. So it basically cast into a film or a gel-like structure, which is result of which is nothing but a quasi-solid state, which like ultimately result into a quasi-solid state electrolyte, which is soft, stretchable, and it provides a conductivity of in the range of 10 to the power minus 3 to 10 to the power minus 2 Siemens per centimeters. So it's like highly compatible with low cost fabrics, and what we say is the variable integration, like in the watches or in those things. So and uh, so the ion transport mechanism, as I mentioned, the polymer chains are using the functional groups, right? So hydroxylamide, which coordinates with the metal ions like Zn2 plus. So all these things enables this polymer-based fabrication strategies are very fundamental and effective strategies. So the common examples are PVA, PEG, or PAM, PEO, and KCF, which is copper carrier. So this is the diagram which is of a common biopolymer matrix which is used in QSACs. So basically here we see the repeating molecular structure of kappa agarigine, which is nothing but a natural polysaccharide. So it extracted from the red seaweed, and it is widely used as a biopolymer matrix. So in quasi-solid state electrolytes, particularly for zinc ion batteries, so the structure consists of alternating galactose units, which is alpha 1 to 3 and beta 1 to 4 glycosidic bonds. So which makes the kerosene highly suitable for electrolyte applications, like in the presence of hydrophilic functional groups. Also, it contains the hydroxyl groups, the OH groups, and the sulfate O3s minus groups, which induces negatively charged and water uptakes. So it also makes the good coordination with Zn2 plus ions. Then after this, we come to the next fabrication strategy, which is Kappa plus rice paper based QSACs. So basically, it is a bio-inspired fabrication techniques in which building on polymers such as let's say which is made from a Kappa agarigine and rice paper fold. So Kappa agarigine is nothing but a mixture of gelling polysaccharide and thus usually water, and the Kappa agarigine is extracted from red wheat, as I mentioned, right? So the rice water is added to maintain the like the stability of it, the maintain the porous nature of the solvent, so that the absorptions of the ions can be done easily. So the fabrication process for this begins by preparing a cake reagent solutions, which is then soaked into a rice paper substrate, so that there is a pores are available on the substrate. This is scaffold structure, so not only provides mechanical strength but also promotes the electrolyte uptake. Then it is soaked electrolyte, typically ZnSO4 and MnSO4 interacts with the sulfate and hydroxyl group of carrageen. Now this metal is of making a QSSC is extremely high conductivity. It's of order 3.32 into 10 to the power minus 2 7 per centimeter, and an energy density of 400 watt hour per kg. So it is highly bendable and retains 95% of capacity after 300 folds also, and is ideal for a skin electronics like what we can see in the future. So it, as I mentioned, its components are biopolymer matrix like Kappa agarigine, scaffold rice paper to maintain the porous nature of the solvent. Then we have electrolyte as NSO4 and MnSO4 basically to get the metal ions from this. The how it works, I have mentioned, as I explained, it's sulfate and hydroxyl groups in Kappa agarigine, which creates strong Zn2 plus coordination, suppressing dendrites and parasitic reactions. The this is a structural and electrochemical iteration, so it helps us in analyzing. So the red one you are seeing over here is basically a pure Kappa agarigine, and when we see the blue one, it's a Kappa agarigine in the inner electrolyte. So if you can see, the Kappa agarigine pure has a peak of 344 basically wavelength which is there. What I want to you guys to look into is like basically the peak for when a solvent is added rose to 1620. Here is 1640 for C double bond O, C bond O, C single bond O bonds, which inspires like how electrolytes affects the how adding of electrolyte into copper solution affect the wavelengths of the solutions. So this is one example for that. Now next technique is dual PAM PVA hydrogel QSAC. So it's like a fabrication system using a free stroke cross linking cycles where PAM and PVA are formed two interpretending networks. So this technique enhances stretchability, toughness. So the material can stretch up to like approximately 1400 90% and possesses self-healing ability, which is like one of the most important feature of this dual network PAM PV hydrogels. So that is why the ability due to reversible hydrogen bonding, right? So the additional the hydroxyl bonds and the amide groups which interact with Zn2 plus N ensures high ionic conductivity. These properties make this hydrogel ideal for applications such as soft robotics, biosensors, and flexible power patches. So as we go in future in time, so these kind of fabrication technique which will be used in the soft robotics parts. Let's say to move an arm, certain arms require small batteries. So for there, if you want, you can have a flexible battery which can move around. And to have that efficiency, these kind of fabrication technique will have that quasi solid batteries, and this can help in the overall achievement of good efficiency of the batteries. So as I mentioned, so it mechanism goes like cross-linking mechanism, dual network structure, which stabilizes the gel and distributes mechanical stress. Functional groups, amide functional groups like amide CuNH2, hydroxyl OH groups on PAMPV, which coordinates with Zn2 plus ions, promoting the fast ion transport. So this is one comparison of how electrochemical resilience is coming. So in the first base, we can see there is no such effect on the of the bending on the electrolyte. When we come into the bending part of it, then we see the second part in which we can see that GCD, basically galvanostic charge discharge profiles under bending. So it shows that charge discharge voltage profiles vary under the same bending angles. We can see that even after bending at 90 degrees, the curves do not collapse, right? so indicating that hydrogel QSSC retains its electrochemical integrity and capacity delivery using under mechanical strain also. The C part, you can see the repeated bending cycles at 90 degrees, right? So basically, these are repeating bending parts which are coming at 90 degrees. So in this, after 4 cycles of repeated bending, the battery still remains stable and capacity, right? And Coulombic efficiency, right axis. You can see in the right axis the blue squares, right? This shows the Coulombic efficiency of the battery, which remains constant throughout. This shows that even in aggressive and or you can say repeated deformation, it doesn't decrease the electrolyte performance, right? Coming to the next part, which is cutting and self-healing test. It's like a static test which the author of the paper presents. So hydrogel is cut into 2 to 3 4 pieces, right? Then it rejoins with adhesives. Remarkably, after healing, the battery recovers its electrochemical capacity, which is nearly matching the original performance. So this proves that the hydrogel structure is physically reconfigurable and self-healing at the room temperature, which is one of the most interesting part and the area of interest which most of the people are looking into when they are doing this all QSSEs things. And self-healing such a property that even in a battery, if you can have a self-healing part, then the efficiency of using the battery, the shelf life of the battery will obviously increase. Then coming to the last part, which is multiple cut heal cycles, which is dynamic nature. So basically, after each cut, there is small drop in capacity, and after healing, capacity recovers almost fully. Right in the graph, you can see that it is when the recovers, it almost recovers fully. Even after the third cut and healing, performance remains highly stable. So this basically overall thing is to show that this fabrication strategy is very highly important when you say when you are want a battery which uses electrolyte which is self healable, so that you can use it for longer period of time. Coming to the next part of the fabrication techniques, which is gel ionic liquid based QSSCs. So gel ionic is basically it uses ionic liquids such as LiTFSI, LiPF6 and others that are embedded into polymer matrices like PVA, PEG. These ionic liquids offer a wide electrochemical stability window and excellent thermal stability, right? They are combined with polymers to form printable, moldable QSSCs. So basically, these can be used in the gels, which are or electrolytes, which can be formed into a printable things, and also we can use into the molding part of the batteries, so that whatever the shape of the battery, these can be easily fit. For example, in one system, let's say if LFTAC is infused into a PVA PEG gel, producing a flexible QSSI solute suitable for direct ink writing. So these are specially, so basically as I mentioned, it is majorly used in printable 3D printed batteries. So when you design a battery and you want to go 3D printing of the batteries, this kind of fabrication techniques is highly appreciated over there, where complex geometries and soft communications are needed. So these type of fabrication strategies comes over there. So it consists of two parts, which is MOF GE and PVA PEG plus ionic liquid composite. So MOF GE is basically magnetic cellulose nanofibral gel. So it is nothing but basically fabrication involving a soft hydrogel that adapts the surface morphology of the metal electrolytes, such as zinc or some other metal. Then during cycling, what happens is MOF-G conforms the electrode surface, thereby minimizing dendrite formation and maintaining ionic contact. This is critical for high current zinc ion batteries operating under deformation. So MOF-G offers like high cycle life and low polarization of the battery poles, and even when subject to bending on pressure, it provides a good efficiency. Next is next in this is PVA-PG's ionic liquid. Is nothing but again it's a ionic liquid which is infused like as LFITs as I mentioned earlier. So it maintains a stability for 3000 plus hours of zinc plating or stripping, and capable of operating under mechanical deformations and thermal cycling. So this is one example how in 3D printing you can see like it can be used. So if they are using carbon CC or silver and CC, LTO anode, LFP cathode, GPE, packaging. So all these are the steps which are used when they are designing a 3D printing for the batteries. Printable. So basically these are printable ionic liquid infused QSSCs used in DIW based lithium ion battery fabrications. So it demonstrates customizable shapes and configurations for variable electronics. The next one is hybrid organic QSSs. So hybrid organic QSS is like a reinforced with inorganic fillers to improve the mechanical and electrochemical performance. So one such hybrid is the HNT PAM composite, where halocide nanotubes basically are disposed with a PAM hydrogel, and HNTs offer structured rigidity and high surface area, helping regulate in ion pathways and increasing the let's say what we say is mechanical robustness of the electrolyte. So this composite retains over 92% capacity after 1000 cycles also, and offer improved safety and durability for harsh variable environments. So for example, if you want to implement a watch which uses this kind of fabrication, you can easily use it because it has a good durability in harsh environments. It can be very strong when it comes to take pressures or something. So for example, people do drop test and or something. So these kind of fabrications are very useful for making a strong battery structure, so that the battery or the electrolyte of the battery doesn't get affected. The next one is which is basically the last one of this. Morph and cough based skin inspired QSSCs. So these are skin QSSCs. So Morph is basically, as Sudhanshu mentioned, metallic organic frameworks. COF is basically covalent organic frameworks. So what happens in this is basically we take the so this type of fabrication takes the inspiration from the human skin. So these systems are used as a dual layer design. Let's say like how the skin goes for layers of tissue like cells, then covers the tissue, then comes the skins, right? So it works like this. So you have a inner hydrogen layers which is combined with the outer of CUF membranes. So sometimes reinforcements with nanofibers also is included in this. So these CFSs have nanoporous channels that selectively allows zinc to pass. Like how in lithium cobalt battery, the SEI layer allow only plus ions to pass. So this COFs have nanoporous channels that selectively allows Zn2 plus to pass while blocking polysulfide shuttling. So this is one of the drawbacks of various uh, batteries which uses sulfur into their anode part or cathode part. So it also blocks that polysulfide shuttling and in Zni2 batteries also. So the fabrication includes layering and and cross-linking techniques to create asymmetric structure. These electrolytes show promise for polysulfide blocking, moisture retention, and safe long-term variable storage. Yeah, so this is the one example of how HNTPM gel metrics enhancing ion transport and durability. So let's say this is how the skin looks like, and this is how they are trying to frame. So providing one hydrogen layer, then one layer above it. So this is biological inspired skin like asymmetric structure of a functional CF nanopolymer. So with MOF CF architecture demonstrating selective ion getting and mechanical resilience. So this is the summary table of all the fabrication techniques. So as we see, polymer-based QSSI fabrication techniques is PVA PM uses PBA PM PO, and it keeps it simple and flexible, printable. So this can also be used in that. Now coming to ionic energy, it offers the ionic energy of the order 10 to the power minus 10, so Siemens per centimeter. It generally used in flexible devices. As I mentioned, this is one of the batteries which will be coming more fastly in the watches or in whatever wearable devices. Then this Kappa Kirigan plus rice water solution electrolyte, which was KCr plus ZnO, so for resin electrolyte soaked, in which the KCr is soaked along with the rice water. Then features are it is biocompatible, it is mechanically good, stable, and the ionic conductivity is very high as compared to other fabrication techniques. 3.32 to the power 10 to the power minus 2 Siemens per centimeter, and it is ES stable. JIBs and you can use it into the outer variables also. PM, PVA, hydrogen. This technique uses cross-linked in PM, PVA as I mentioned, and it was a good stretchable part. And self-healing is one of the important feature of this particular fabrication techniques. It provides the kinetic conductivity of approximately 10 to the minus 3 to 10 to the minus 2 Siemens per centimeter, And as I mentioned, since having a self-healing part and stretchable parts, it is highly applicable in soft robotics, or if you want any e-skin. E-skin is nothing but basically if you want, let's say, prosthetic parts of the bodies, you can use in that gel anionic liquid. PVA PEG, which is using LFTSI, as I mentioned, electrolyte solvent. For MOG is CNS. So it's basically magnet active dendrites. It also enables dendrite separations. It is magnet active, and it provides the kinetic conductivity of up to 10 to the power minus 2 millisiemens per centimeter, which is a bit less. Now then comes to 3D printing. So basically that's why it is used in 3D printing of the flexible batteries. Then comes the HNT PAM composite, which is PAM plus halocide nanotubes, and it enhances the durability, as you mentioned, according to ZN2 plus regulations. And the but like ionic conductivity for this is basically very high. The exact number for this is still not figured out because it varies depend on the reactions which we are using. Then it comes to rug variables, long-lived ZIBs. Then comes to skin-inspired QSSGs, which we saw in the last slide. So basically, it uses COF members plus aramid neutrophils. So basically, what happens? It uses the human biological aspect of designing the electrolyte. So basically, inner hydrogen layer then covered with the uh, of membrane, then providing a aramid nanofilament filters. So asymmetric. So it's basically asymmetric and blocks polysulfates, surface shuttle reactions, shuttle effects. Then comes the controlled ion gating. Then applications is ZnI2 batteries in textiles.
I'm going to walk you through some of the key synthetic techniques used for QSs. First is 3D direct link, freeze that cross link, ensued polymerization, solution casting, sol gel synthetic for ionic and conductivity, and electrospinning and solution casting. Next slide. So we will go one by one. With the 3D direct ink writing, this is an additive manufacturing of 3D products technically that allows research to print uh, customized QSs structure using specific formula inks. These inks are typically composed of polymers, matrix combined with iron, liquids, or salt. And mechanisms include in DIW, the printable QSS ink is extruded through a nozzle under controlled pressure and temperature. Its application include one major application is in printing ionic liquid-based QSs directly into battery sheets. This is especially used for flexible or wearable electronics where battery design need to conform to irregular shapes. Its benefit includes enable personalized battery architecture, support non-planar geometric, making it ideal for curved or wearable devices, allow rapid prototyping, helping research quickly irritate and optimize designs. Integrated design into device manufacturer, ideal for flexible and integrated device. Second, we go with freeze char cross linking. Next, so its mechanical involves subject the polymer solution to repeated freezing and thawing cycles. During freezing, eye crystals and push the polymer chain those together upon throwing. Physical hydrogen bonds or crystallines are formed between chain action and physical crossing. Its application includes used to create dual network QSs that are self-healing, stretchable, and having high mechanical integrity. Its advantage includes non-chemical cross-linking requirements, create highly porous structures, greatly enhance mechanical throughness. Next slide. Third, we have in-suit polymerization. Its mechanisms include monomers and cross-linkers are introduced in liquid form directly into battery's housing. Polymerization is then initiated with the battery either thermally, chemically, or by UV lights. Its application have used in lithium ion and zinc ion QSs, where ensure uniform coverage and minimal interaction resistance. Its benefits include excellent interface adhesive as the polymer forms in a direct contact with electrode surface, fill all voids and cracks, reduce electrical resistance and safety hazards, compatible with scalable manufacturing methods, include roll-to-roll fabrication, making it industrial viable. Then fourth, we have solution casting. Solution casting is one of the most straightforward and communicable use techniques in laboratory scale synthesis. It involves dissolving in a solvent along with an electrolyte salt such as LiTFSI This solution is poured into a mold or flat surface and allowed to evaporate slowly, forming a thin film. Its applications include polymer salt matrix QSs, including systems like PVA, PEG, LICL films, and biodegradable QSs. Its advantage have simple and cost-effective form lab scaling testing, produce homomorphic uniform films with good ion conductivity, easily customized with different polymer salts and even monofilm like silicon or graphite. Next slide. Now, fifth synthetic technique is Sol general process. Is a chemical method that help introduce ceramic or inorganic phase into polymer matrix for improved QS's performance. This method involves hydrolysis and condensation of metal organic precursors like alkyl oxides to form a stable gel. Its applications are in creating MOF-based SiO2, TiO2 embedded QSs. Its benefits include enable non-structural control, ideal for tuning ion pathways, offer enable thermal and chemical stability, and promote uniform ion conductivity, especially in mixed ion batteries. Next. Now we have electrons spinning and solution. Last but not the least in electrospinning, often combined with solutions casting for creating porous non-ferric mats. Its mechanics include high voltage is applied to a polymer solution, ejecting fine fibers that are collected on a substrate on a on-wear mat. Its application includes QSs are ideal for breathable, wearable device and are also used in high-rate zinc ion batteries. Its advantages are extremely high surface area, increases electrolyte interface, promote multi-directional ion transport, and excellent for breathable and wearable electronics. Next slide. So, firstly, I will go through with the diagram. So, diagram on left y-axis we have specific capacity. On right of y-axis there is a Coulombic efficiency, and on x-axis represent a cyclic number which goes beyond 400. So what the graph interpreted is the Coleman efficiency remain very close to 100% throughout the cycle, which indicate excellent charging retardance and minimal side reactions as sign of stable electrochemistry. Now, what the description says ki uh, the ionic conductivity. KCR based QSs have a conductivity of 3.32 into 10 to the power minus 2 per centimeter, and PAV PVA gels reaches 6.7 megascales per centimeter and scratch up to 1490%. Electrochemical stability windows. Aqua hydrates have 2 to 3 volt of aqua hydrogel, and organic gels have range of 4.5 to 5.2 volts. Ionic liquid composite reach to 5.5 volts, sustainable for high voltage battery chemistries. Now we have long cycle life. Some QSs have demonstrated over 3000 hours of stable zinc plating. Now we have self-healing and dendrite surplus. Material like PMW, PVA gels are self-healing, meaning they can automatically restore their structure after damage. Next slide. So mechanical and thermal properties. Mechanical flexibility. It implies that QSs show high endurance to repeatedly bending and even cutting. Stropom mats and GAD firms can stretch, twist, and deform while retaining ionic conductivity. Thermal stability or thermal performance. Most QSs function stable across minus 20 degrees Celsius to 80 degrees Celsius. Thermic field QSs show only a 5% drop in conductivity even after 100 hours at 80 degrees Celsius. Self-healing behavior. QSs like PAW, PVA automatically heal cracks that occur during charging, discharging cycle. The graph here represents a examine the mechanical flexibility of a QSS under different bending conditions. Here, y-axis again show a capacity, and x-axis shows the number of cycle up to 50. Different color represent different bending angles. Green for non-bendings, orange for 60-degree bendings, and purple for 90% bending. What is interpreted is the three curves begin with similar capacities. However, as the bending angle increases, the drop in performance is slightly more notable. Even at 90-degree bending, the battery maintenance a capacity above 180 degree after 50 cycles. So next slide. Here are the applications of QSs. First, flexible and wearable batteries. QSs are revolutionizing wearable technologies by enabling bending and flexible power sources. They can power devices such as smart textile, health monitoring patches, and electronic e-screens. These electrolytes maintain stable electrochemical performance even under extreme mechanical stress. For example, QSs based on Kappa Courageous and rice paper was shown to retain 95% in its capacity. Biocompatible on skin electronics. QSs can be made using non-toxic biodegradable polymers like KCR, cellulose, and other natural materials. These makes the suitable for epidermal electronics, implantable medical devices, and biosensors. Third is printed shapes confirmed power systems. Thanks to advanced like 3D printing and direct linking writings, QSs can now be fabricated into customer shapes. This is ideal for embedding power systems and non-planar device designs. Support large by layer battery constructions, making it easier to integrate power directly into soft electronics. Fourth point is highly safety energy storage. QSs offer enhanced thermal and chemical safety compared to liquid electrolytes. They are non-flammable, leak-proof, and can operate across a wide temperature range from -20 degrees to 80 degrees Celsius. Self-powered IoT and smart system. Its use distribution sensor network, RF devices, and wearable AI can recover from mechanical damage, cut in and support automated operation. Example: PAWPA hydrogel QSL power devices after multiple cuts and repair. Next slide. So here are some challenges of QSs. First, scalability. More QSs use expensive materials such as ionic liquid or metal organic frameworks. Currently, manufacturing methods are often batch-based, making them unsuitable for mass production. Long-term stability. Water evaporation in hydrogel-based QSL limits their shelf life. Zinc dehydrate group and corrosion remain significant issues, and especially in zinc-based synthesis. Performance trade-off. There is often a compromise between high ionic conductivity and mechanical robustness. Strengthable QSs may lack ionic pathway while regards other resist deformation. Further discussion, we have model and customized QSs. 1 minute. Need for optical testing and self-healing and self-registration system. Next. Uh, now we now we have further directions. So modular and customized QSs. Further QSs may be application specific with tiered flexibility, conductivity, and shape confirmation. We have smart electrolytes. Smart QSs may feature adaptive stiffness, built-in sensitive mechanism, and polymer and associated for selective ion transport. AIML material design. Mechanical learning it's being employed to predict electrical performance, optimizing composite and accelerate recovery. We have adaptive testing and direct ink writing plus discovery architecture. Eco design plus closed loop manufacturing. Next. Now sustainability aspects. Biodegradable polymers used for natural renewable material like aggregates, carbonatates, and chitinose. Green processing. Perform for water-based, solvent-free, and energy-efficient fabrication process. Life cycle analysis. There is a growing need for full LCA for material extracted for device disposal to ensure the entire process is eco-responsible. At next page. Now we have to summarize. So we have the conclusion includes QS's solid state electrolytes are a promising bridge between liquid and solid state batteries, often offering flexibility, safety, and consumality. These integration into wearable biocompatible devices, 3D printing batteries, and IoT system demonstrate their immense application scope. Properties like self-healing, thermal resilience, and the edge in emerging technology. However, challenges is scaling cost and long-term stability must be resolved throughout smart material AI-driven devices, and suitable manufacturing. Ultimately, QSs represent a realistic and transformative solution to power the flexibility electronics resolve into the future. Next slide. So here are the references from which we have developed our research. Here are the around we go around 43 research papers and concluded our research for QSs. Thank you.
Thank you, everyone.